All right, guys, Mr. Antonucci here, and continuing on with section 2 of chapter 8. Here we want to talk about what happens if you have to do regions that are with respect to the y-axis. Now look at our region here. The boundaries are kind of like vertical in a sense. If I put a vertical rectangle in there, it's not going to work because the top and bottom um, are either the function. Like, let's just look here. I could put a rectangle here, here. If I put it here, and then over here, it just gets really weird. So, um, in some cases, it's easier if you put your rectangle like this. Okay, so if this is f of y, a function of y, and this is g of y, then the area of that little rectangle, well, is going to be base times height, where the height of the rectangle corresponds to delta y, and the base is um, is from this x value to this x value. So it'd just be x2 minus x1. Okay. Now, since this is a function of y, I could think of this as f of y, x2 or f of y2 minus f of y1, or excuse me, g delta y. Okay. Now that's going to give me the area of that one horizontal strip. If I add them all up, equals 1 to n, um, then that would give me the approximate area of that region. And then again, if I take the limit as n approaches infinity, that's going to give me the exact area of that region. But remember, when you take the limit as n approaches infinity of a Riemann sum, you get a definite integral. So the area is going to be the integral from c to d of f of y minus g of y dy. Notice you're integrating with respect to y. I like to tell students that you're going to do right minus left because you're not talking about top and bottom boundaries. You've kind of like have to tilt your head to the right and think of it like that. And it's going to be the right boundary minus the left boundary. So if we want to do this one, we have the area of the region bounded by the graphs of y plus 2 and y squared right here. So the first thing we need to do is find the intersection points of this. So we would have f of y equals g of y. If you're allowed Desmos or a calculator, you could do it on there, but that would be y plus 2 equals y squared. So y squared minus y minus 2 equals 0. And then we could factor this into y minus 2 times y minus 1 and get y equals 2, y equals 1. And that would correspond to that point and that point there, the y value there. So this is -1 and this is 2. So the area is going to be the integral from, that would be, oh, this should have been +1. So this would be -1. So -1 to 2 of the right boundary, which is made by the line, which is f of y minus g of y, then dy. Okay. Then you could anti-differentiate, plug in the 2, and then plug in the -1. And again, make sure you're plugging in the functions y plus 2 and y squared, not just x and x, because you're doing everything in terms of y here. For this one, the final answer would be 9/2 or 4.5 as a decimal there. So there are times whenever you can partition it with respect to the x or the y-axis. So I want to look at an example where that is possible here. We have the area of this region, and it's y equals square root 4 minus 4x, and y equals square root 4 minus x. It's important to identify which one is which, and we want to find this area by partitioning the x-axis and then by doing it with respect to the y-axis. So for the x-axis, I always think if it's going to be with respect to the x-axis, then the strip has to intersect the x-axis so that the thickness of that strip is on the x-axis. So this helps me because if I draw a representative strip, it's going to be a representative rectangle, and it helps me understand how to set this up. The issue here is when we get over to values between 0 and 1, the region is between those two curves there. So when I get over to values between 0 and 1, the vertical strips are bounded by the two functions. Between 1 and 4, the vertical strips are bounded by the blue function in the x-axis. Okay, so the area is going to be the integral from 0 to 1 of square root 4 minus x minus square root 4 minus 4x dx plus the integral from 1 to 4 of the reverse of that. So that's going to be, well, not the reverse of that, rather. It's just going to be 4 minus x dx. Because from 1 to 4, the top boundary is the graph, and the bottom boundary is the x-axis, which is the line y equals 0, but you wouldn't write minus y equals 0. All right. Then we could anti-differentiate, plug in the limits, and subtract, and you would get 4. If we're going to do it with respect to the y-axis, let me erase, oops. Let me erase some of this here for us. I keep erasing my figure. So, well, you know what? We'll just do it in a different color here. So with respect to the y-axis, your strips are going to be horizontal like that. Now notice, no matter where you put the strip, the right and left boundary are still the same. So it's going to be the integral from 0. Now here's where you have to be careful. In terms of y, it's going to be from 0 to 2. All right, because the y values go from 0 up to 2. The other thing is we have to solve our equations to get them in terms of x. So if I have y equals square root 4 minus 4x, then y squared equals 4 minus 4x, and x equals y squared plus 4x plus or minus 4 over 4. All right. And then for the other one, if I have y equals square root 4 minus x, then y squared equals 4 minus x, and x equals 4 minus y squared. Okay. Now, the boundary on the right is the blue graph, which is this function. So in terms of x, it's going to be 4 minus y squared. So now this can help me set up the integral, which would be 4 minus y squared minus 4 minus y squared over 4 dy. I solved that incorrectly. You would have x equals 4 minus y squared over 4. All right, now this is going to be a lot easier to anti-differentiate in this case if you had to do it by hand. Either way, you're going to end up getting 4 for this one. All right, guys, that's it for this one. Hope that was helpful to you. As always, reach out if you have any questions. Take care.